Okay. Let's start. So, reaction kinetics, so kinetic chemistry is about the rate of reaction, right? It's about rate of reaction. In rate of reaction, there are two of the ways we calculate the rate of reaction. How do you calculate? Like, what are the two of the ways where you calculate the rate of reaction? Yes, yes. So it's either rate of consumption of reactant or either rate of production of products, right? You can either calculate it using the consumption rate of the reactants or the production rate of the products. That is two way. So now kinetic chemistry. Whose pen is this? Bro, catch this one. Yeah, I have got your pen, so where's my pen? That's in the pocket. Yeah. So kinetic chemistry. So reaction can happen in two of the ways. A, B into C. Let's say this is the reaction. So this rate of reaction, right? Rate of reaction can be measured in two ways. One is rate of reaction can be calculated in two ways. One is rate of consumption, that is depending on the reactants. The second is rate of what? Production. These are the two ways. Either a rate of consumption or a rate of production, right? And if it is a rate of consumption, right? And if it is a rate of consumption, we'll take the whole thing into one box, shall we? Now, we'll take a common formula. So this is the common formula for the rate of reaction. First, like know that rate of reaction is measured final minus initial amounts, right? Divide by time. This is the common equation. These final and initial amounts are calculated either in moles or concentrations, right? These final and initial amounts are calculated either in moles or the concentration, right? So if I put that all in one box, in moles, in concentration, and rate of consumption, that will be rate of consumption will be let's say A, rate of consumption of A is equal to RA equals delta in for the constant the mole difference of A divided by time, right? And because it's a rate of consumption, we understand that because it's a rate of consumption, always the final amount of A is less or more, is less. Final amount of A is less. Initial amount of A is more because it's consuming. The A is reducing, right? So the final amount of A is less and the initial amount of A is more. So final minus initial will give you a minus value. So the rate of consumption is also always a minus value. Therefore, to make it a plus value, what do? You have to multiply this by minus. So RA equals minus delta N over delta T. Minus is there to plus the value at the end. Okay? Right. And if it is concentration, that will be RA equals concentration difference. There should be minus again, minus concentration difference of A divided by time difference, right? And the unit of this will be mole per second. This will be mole per decimeter per, right? And rate of consumption of B will be same. Rate of consumption of B will be same. And if I come to rate of consumption, rate of consumption, sorry, rate of production, rate of production. I'll take C. The C is the only product, right? Rate of production of C. That is RC. Does it have to be minus? No. So it's delta N divided by delta T. Gives the rate of reaction. And if it is concentration difference of RC, that will be delta. Concentration is always like in this square bracket. So it's delta A. Sorry, there doesn't have to be a delta. A concentration difference of A divided by delta T. This is again mole per second. This is mole per decimeter per second. Correct? Right. These are the two equations that you're supposed to use. Right. It's always final minus initial. Final minus initial. So depending on the reaction, you have to put final value minus initial value. Right. Understood it? Shall we go to the stoichiometry of the reaction now? C. It's C. It's C. Not A. N. Because the product is C. Yes. The next is stoichiometry. So now we have to consider, uh, in the beginning, like we just wrote the equation of rate of reaction, final minus initial divided by time that was spent. But when it comes to the stoichiometry, now the stoichiometry is also affecting the rate of reaction, right? Stoichiometry is also affecting the rate of reaction because the stoichiometry changes the amounts that react and amounts that produce will also, right. So stoichiometry of a reaction. Uh, so I'll take something like this. Let's say 2a plus b produces 3c plus uh, 4d. I'll take it this way, right? So now this is how it happens, right? Let's say initial reacting and final values should be there, right? So this stoichiometry is mentioning how much of a proportion is reacting, and after reacting how much of a proportion, how much is produced, right? And how much of a proportion is reacting in how much of a proportion of the other reactor, right? One example is I'll give you, like let's say there's 1 mole of B at the beginning, right? So for that to completely react, how many moles of A is necessary? This is 1 mole of B. For this 1 mole of B to react completely, how many moles of A is necessary? That is when the stoichiometry is coming. The ratio between B and A is 1 to 2, which means what? To react 1 mole of B, you need 2 moles of, get it? To react 1 mole of B, you need 2 moles of A. So to completely react 1 mole of B, you need 2 moles here, right? 2 moles of B, get it? And if 2 moles of A and 1 mole of B reacts, there will be how much of C? 3 mole of C. Because 1 mole of B, if completely reacted, they're supposed to be 3 mole of C. Correct? And how many moles of D should be there? 4 moles of D is also produced. But at the beginning, there's no COD produced because there's only reactant. So now in the first part, look at this. So there's 1 mole and 2 mole of each. 1 mole of B is there, 2 mole of A is there. So you can completely react with each other. Okay? Nothing is lacking, nothing is more. So they completely react, which means when it comes to the reaction, 2 moles of A will react with like complete 2 mole of A will react. That's how we write it, 2 mole minus 2 mole. Like out of 2 mole is reacting. That's what I'm writing. Out of 2 mole, 2 moles are reacting. Reacting. Out of 2 mole, 2 mole are reacting. Out of 2 mole. And out of 1 mole of B, 1 mole is, out of 1 mole of B, 1 mole is reacting. And how much has produced? 3 moles of C is produced, 4 moles of D is produced. Understand that? Because stoichiometry complies with each other. Ganda theme. So the reaction and the like the stoichiometry and the amounts are same. Right? And at the final part, the whole 2A is completely reacted. So there's no A there. And whole B is completely reacted. So there's no B there. And 3 mole of C is produced, 4 mole of D is produced. That is the final. Get it? Yeah. And come to another part of this. Come to another part of. Oh, nothing I did. That's a stoichiometry. If this is in the same amounts, this will be in stoichiometrically 3 and 4. A amounts में तीन हो ना මේකෙත් A amounts में හැදෙන්න ඕන. ඔව්. එහෙනම් මෙයාගේ 1 mole මෙයාගේ 2 mole තියෙනවනේ. stoichiometry එකත් 1 to 2 නේ. එහෙනම් මෙයාගේ 3 to 4 හැදෙන්න ඕන. amounts. Right? amounts ඒ ගානම හැදෙන්න ඕන. Right? So, I'll like change the situation now. Right? Let's say initially දැන් මේ stoichiometry එකටම තිබ්බනේ. දැන් stoichiometry එක පොඩ්ඩක් change කරනවා. හරිද? Let's say initially there's only 0.5 moles of B, right? So to completely react with this 0.5 moles, how many moles of A should be there? 1 should be there, because like if this is 1, there should be twice the amount of A. So if there's 0.5, there should be how much? 1 mole of A to completely react. Completely react B, there should be 1 mole of A. Get it? And reacting. And in reacting, so if this is under the stoichiometry, 1 mole will completely react. Out of 1 mole, 1 mole will completely react, because this is complying with the stoichiometry. And out of 0.5, 0.5 will react completely, right? And how much of C will be produced? How much of C will be produced? How much? 1 to 3. So if it is 1 to 3, 0.5 to how much? 3 times of it, right? 0.5 to 3 times of it. That means 1.5 mole. And how much of D? 1 to 4. That will be 0.5 times 4. That is 2 mole. Get it? Yeah. That's how it happens. So the final will be this will be 0, this will be 0, this will be 0 as well, this will be 1.5, this will be 2, right? That's a final. Get it? I'll go to another. මම පොඩි කරන්නේ මම මේ උඩට කරන්නේ උඩට ගන්නකොට පොඩි වෙනවනේ. එහෙම තමයි යන්නේ. ඒක අර තිබෙනවා. එතන කියන්නේ ලොකු වෙනවා. මම හිතන්නේ. ඔබ වෙනස එන්නේ. විතරක් ගියා නම් හරි ඔව්. I think I might be not. මට ඒක notice වෙන්නේ නැතුව වෙනවා. හරි බලන්න. So this is the other one. Initial. Let's think 0.5 of B is there, right? And in this time, like I'm not taking the amount of A that needs to react completely. Instead, I'll take like any sort of amount. Okay? I'll take any sort of amount. That let's say there's 2 moles of this, right? There's 2 moles of this. Only 0.5 moles of B is there. Now, how much is reacting? Can this 2 mole completely react? No. Why? Because only 0.5 is there. So with 0.5, how much can react? 1 can react, right? So in that case, 0.5 becomes limited. Call it the limiting factor. When it comes to a reaction, limiting factor is very important. Even in the standard heat of reaction, sometimes one factor becomes limiting. That limiting factor actually decides how much is reacting, right? How much is reacting, and depending on how much is reacting, how much of heat is produced is also considered. So therefore, when it comes to the standard heat of reaction, delta H naught equals Q over N. The N should be the limiting factor. Should be the limiting one, because that decides how much is reacting. How much is reacting decides how much is heat is. Okay? So reacting out of 2 mole, how much can react now? Only 1 mole can react, right? And out of this 0.5, 0.5 will completely react, because that's the limiting factor. Now, which one decides how much is producing? Is it 2 mole or 0.5 mole? 0.5 mole, because it's the limiting one. It decides how much is going to produce. So how much of C is produced? 1.5 is produced, because it's 1 to 3, 0.5 to 1.5. And how many D's are produced? If you take the final, there's 1 mole of A left. This is completely reacted. 1.5 mole of C is produced and 2 moles of D is produced. Do you understand that? That's really important. This part is really important about the stoichiometry, right? How much is reacting with how much is produced. So depending on the stoichiometry, the limiting factor, everything can change, right? It's simply like achcharata mechcharana mechcharata kochcharata sort of a thing. So if you know the stoichiometry, and value of either one of a reactant or product, you can guess all the other products and reactants reacted, right? ඔයා හැදිච්ච ඒ කියන්නේ reaction එක complete වෙන්න හොඳේ. ඔයා එකක හරි දන්නවා නම් මෙච්චරක් හැදලා තියෙනවායි කියලා. අපි අපි B ගේ කතා කරේ, B ගේ 0.5 තමයි react කරලා තියෙන්නේ. That's the only point we have. And we know the stoichiometry. We can tell all the values that have reacted and produced. හරි. හැබැයි ඒ stoichiometry එක completely තිබ්බොතින්. ඒ කියන්නේ දැන් 0.5 එක 1 නේ react කරන්න පුළුවන්. Sometimes there can be 2 moles of A. We don't know. But only one will be reacting. හරි. එතකොට මේ reaction එකේදී අපි කියන්නේ how much is reacting කියන එක තමයි බලන්නේ. How much is reacting, and depending on how much is reacting, how much is produced. මේක අපිට කියන්න බෑ. මෙයා විතරක් දීලා තිබ්බොත් මෙයා 3ක්ද 5ද තියෙන්නේ කියලා කියන්න බෑ. ඒ මෙයාගෙන් 1 විතරයි react කරන්න කියලා අපිට කියන්න. ඒක තමයි ඔකෙදි කරන්නේ. Right. Okay. So now that is about stoichiometry. Is it heavy? Is it heavy? Like too much of information. 10 minutes. Right. So that's about it. Right. So depending on that, we have to, calculate the rates of reaction. What are you looking? Okay. Right. So if we take the rate of reaction, right? If we take the rate of reaction of, let's say the final one, right? Final. I'm taking the final one. So I'm writing the rate of reaction. There can be 4 rate of reactions, right? Because there are 4, like 2 reactants and 2 products. So for those 4, we have to have 4 rate of reactions. So now let's calculate the rate of reactions of those 4, right? So rate of reaction of A. So we took it in moles, right? We'll take delta N over, take delta N over delta T. So tell me RA. Now if I take RA of the final one, mame final එකේ ගන්නේ. What is the initial and the final? A ke final 1 mole, initial 2 mole. B final minus initial. අන්තිමකට හදන්න. පළවෙනි එකට නෙමෙයි අන්තිමකට හදන්න. Right? So it's final minus initial. So there has to be a minus here. There has to be a minus here and put it there. So minus, tell me the final. That is 1 mole minus initial is 2 moles. Let's take time spent is 1 second now. Take it that way, right? And the rate of reaction is what? 1 mole per second, right? Is 1 mole per second. Let's take RB now. Take RB. If it is RB, that is also a reactant, right? So minus delta N over delta T, right? Delta N over delta T. And minus what is delta N now? Final is where is it? Yeah, B. Final is 0, initial is 0.5. So final minus initial, right? Final minus initial. Final minus initial. Final is 0 minus 0.5 more. Time will take 1 second. So the rate of reaction is how much? 0.5 mole per. And if I take the RC, RC delta N over delta T. You don't have to put minus here because RC is a product. So what is the final and initial of RC? 1.5 is the initial. No, initial is 0, right? Sorry, not this one. Initial is 0. Right? So initial is 0, final is 1.5. Initial is 0. Is it? No, final is 0. No, I'm sorry. So yeah, final is final is 1.5 mole and initial is 0 and the time spent is 1 second. The rate is 1.5 mole per second. Correct? Right? But second a minute is more or less minus 1. Right? So next is R T. The concentration. Yeah, we get number of moles. Sorry. Concentration mole per decimeter per second. So RD, what about the final RD is like delta N over delta T and RC initial 0, final is 2, right? So it's 2 mole, final minus initial 0. 1 second. So it's 2 mole per second of a rate. Now, do you see that this has like 4 different rates of reactions, and why has it changed? Why has it differed? Yes, because the stoichiometry is different. So when you have different stoichiometry, if you take the rate of reactions, they are different. And if you have same stoichiometry, they have the same rate of reaction. Get it? And in these cases, right, the leftover were there, right? Leftovers were there, but like we didn't consider the leftover, we just took the final and initial, which means how much has reacted. That means like leftovers can be there, doesn't matter. Things will only react according to the stoichiometry and depending on how much is reacting and how much can be reacted, right? How much is reacting and how much can be reacted. 0.5 is reacting, 1 can be reacted, 1 is left, right? That is what happens, right? So this is the rate of reaction, normal rate of reaction. Understood it? Question, if you like have any doubts, questions, feel free to ask. Huh? Good. That's rate of reaction. Right. So the next is average rate of reaction. Right? Average rate of reaction. Right. Next is average rate of reaction. Average rate of reaction. Right. The average rate of reaction is a common reaction for all the reactants and products, independent from the stoichiometry. Right. Average rate of reaction is the common rate of reaction for the whole reaction, which gives the same value for each and every reactant and product, independent from the stoichiometric value. Because the rate, like the rate of reaction change because of the difference of the stoichiometry. The average rate of reaction is a common rate of reaction for all the reactants and products independent from the stoichiometry. So to become independent of the stoichiometry, what do you have to do? You have to get rid of the stoichiometric multiplication, right? Because this was like, this happened because we had to like multiply it by the stoichiometry. So how do you get rid of the stoichiometry? Divide it by the stoichiometry. So the multiplication will, yes. So the average rate of reaction is when you do what? Reciprocal the stoichiometry before the rate of reaction. Get it? Average rate of reaction is when you multiply with the reciprocal of the stoichiometry before the rate of reaction. So as an example, if it is Ra, right? It is Ra, what do you do? Minus you reciprocal the stoichiometry. So it, what is the stoichiometry of A? Is 2. So what do? You put 1 over 2, right? Delta N over delta, get it? And shall I do the calculation as well? I'll do the calculation as well. Huh? It's minus of we have to go all the way. We'll go all the way. Doesn't matter. 1 mol minus 2 mol divided by 1 second. So the final will be 2 to 2 cancels out. Sorry, there's 1. There will be 1 over 2, or it's 0.5. What do you want me to write? 0.5 or 1 or 2? Right, okay, 0.5 it is. Right, 0.5 mole per second is the rate of reaction now. Correct? Right. So if it is RB, what do you do? What is RB? RB is, what is the stoichiometry of B? It is 1, and if you reciprocal it, still the 1. So you don't have to do anything. B minus delta N over delta T, right? So we'll give the same value, isn't it? RB will equal to 0.5 mole per second, right? Yeah. So RC is the next one. RC is the next. RC equals, what is the stoichiometry of RC? It's how much? 3. So it's is it a minus? Should it be a minus? No, it's a product. So just 1 over 3 delta N over delta T. We put the values 1 over 3. Now shall I apply this the complete? Alright, because I applied it here, I'll apply the values now. So 1.5 minus 0. Again 1.5 minus 0 mole and 1 second. Now what will happen? 1.5 divided by 3, that is 0.5 mole per second, isn't it? And what about RD? RD is, yes, because the stoichiometry is 4. That will be 1 over 4 delta N over delta T, right? That is 1 over 4, 2 mole minus 0 divided by 1 second, and the answer is 0.5 mole per second, right? So now what can you tell about the average rate of reaction of 3? 1, sorry, all the 4. 1, 2, 3, 4. Average rate of reaction of all the 4 are same because we got rid of stoichiometric multiplication, right? So all the values are same now. That is average rate of reaction. So when it comes to the average rate of reaction, all the rates are equal because we reciprocal the stoichiometry. Get it? Right. Right. And did you understand the limiting factor? Here this becomes what? This becomes limiting factor. Shall we label it there? This is the limiting factor. The limiting factor. Very important. And limiting factor. Right? Factor. So in average rate of reaction, what do? Reciprocal the stoichiometry before the rate of reaction. Shall we write that as well? Reciprocal the stoichiometry before the rate of reaction, and it gives a what? Common rate of reaction for all. We don't have to write everything, because you have to have understanding and memory as well. So like best short note is you remember many and you write a few that when you look at it, you'll remember everything, right? That's how you do a best short note. Like you don't write everything in a short note. If you write everything in a short note, that's not a short note. Same note, I have like written it in small size. You don't do that. What you do is actually when you're doing a short note, you write things in very short manner that when you look at it, you'll remember everything, right? Because you are writing it. So now in this case, I'm writing it. I get to remember it. I anyways remember it. But best thing is if you can redo it, right? If you can redo it, either you by your own self or try to rewind it or just re-go through it, remembering everything I said. I have to go through the recording again. Okay, okay. Yeah. Now you get it. Huh? Did I tell you that you will get it later? That happens. That happens. That's how you. Very well. So that's how it works, right? And as I said, like you will eventually get there. But the point is, you have to take the action. That's when you grow up, right? And if you didn't take the actions, it will be the same, right? It's all about you taking actions more than I do my stuff. Yeah, yeah. So like we are 50-50, but my 50 is really important, of course. And what is important for me is like your 50. I'm expecting more 50 of you, 50 from you. Because like when you put more efforts, you will understand it more. That's what I'm saying. Like when you make the short note, if you make it out of you what you understood, you don't write everything. You write a few things, but looking at those few things, you'll remember everything. That's how you make a short note. So I didn't write everything in here, right? Just the calculations all, but I see everything inside of this calculation and all. That's what happens. Right. So that is average rate of reaction. Okay. And next is factors affecting the rate of reaction. Right. Factors affecting the rate of reaction. Factors affecting the rate of reaction. Right. Factors affecting the rate of reaction. How many factors are there? 3. What are the factors? Uh-huh. What are the no 3 factors affecting collision? Sorry. Not the rate of reaction. Sorry. Factors affecting the rate of reaction is 4. Yeah. True. Factors affecting the occurrence of a reaction should be the topic. I'm sorry. Factors affecting the occurrence of a reaction. What are the factors affecting the occurrence of a reaction? Collision, correct orientation, activation energy. So when you write it, you'll have to write the total form. So like reactant should collide. Reactant should collide in the right orientation, and yes, and the reactants colliding should have overcome the activation energy difference or the activation energy barrier. Oh, right. Right. Ah, right. Oh, හරිද බුද්ධිපයෝ ඉන්නවද දන්නේ මගේ නම් එක දැම්මම හරි නෑ ඒ කියන්නේ බුද්ධිපය නෑනේ එයාට කෝල් කරොත් එයා නෑ මේ මගේ නම් එක දැම්මම හරි තියෙන හරි only cow okay right so fact is affecting the occurrence of a reaction so when I write the uh, the short note I don't write everything but you have to remember it like the total one. And when you answer the paper, you have to write the total one, not the short ones. So when I write the short note, I'll write just collision, orientation, and activation energy. All enough. But when you write it, you have to remember the reactant should collide. Reactant should collide in the correct orientation. And the reactant should have overcome the activation energy of the 3, right? If I'll just write 3 of it. Collision, right? Second one is orientation. Third one is activation energy, right? Third one is activation energy. So if somebody don't know is studying this, they can't actually get much out of this. You understand? If somebody don't know is studying this short note, he can't get much out of it. Why? Because we don't write. Right? It's not a short note for everyone. Short note for who have joined the class. Right? All the others will confuse or will like won't gain much. And the short notes should be like that. Like after short notes සර්ලා හදනකොට එහෙම නෙමෙයිනේ. ඔක්කොම දානවානේ. That's not a short note at all. Short note should be something like this. And best thing is you make it. Right? Thing is you make it. Because that's yours and you know what is there, and like you know how to like rewire it. Where does it go? Where should it end? You know all of it. Right, okay. Right. So those are the factors affecting the occurrence of a reaction. So when we say factors affecting the occurrence of a reaction, now collision is like what? The example I gave is like plugging a bulb, right? So the collision is the plug and the socket connects to each other, right? They have to like collide with each other. Second is right orientation. If you change the direction of the plug and you try to fit it to the socket, it won't fit in. Right? That's the orientation. You have to like turn it to the correct orientation. Right? It happens randomly. In reactions, the molecules turn randomly, right? Doesn't have a like a pattern. There may be a pattern we don't know. Like it happens randomly. We have to study the pattern. It's a huge thing. Right? And the third one is activation energy, which means when they collide, they have to have this energy for the plug to fit in inside the socket. Otherwise, they don't like they won't will go inside and like will fit in. Yes. So that's activation energy. Those three factors should be there, right? And the next is factors affecting the rate of reaction, right? Factors affecting the rate of reaction. Factors affecting the rate of reaction. There are four now. What are the factors affecting the rate of reaction? Temperature. Okay. Second is nature of the reactants. Okay. Presence of catalyst. You said the first in last. Presence. Oh, if it is gaseous reactants, pressure. Hmm? Pressure. Oh. Pressure volume difference again gases. So like if it is its concentration basically, but pressure for gaseous reactants, right? Pressure for gaseous reactants, right? Pressure for gaseous reactants. And the next is how is temperature affecting the rate of reaction? We shall not write it. We'll discuss it and remember it. Right? So next thing is like when you go through it, when you come to the point temperature, you have to have the ability to memorize it, that this is how the temperature is affected, right? Because you don't have to write it. If you write it, it's again the tute, a paper. So how the temperature is affecting? When you heat it, the kinetic energy will increase. So the probability, yeah, number of collisions will increase. Therefore, the rate of reaction will increase. That is one. So we will remember it in short. When you write it, expand it. But remember it in short. When the temperature increases, number of collision increases due to the kinetic energy increase. Second is again its energy. So the activation energy barrier is not increased, like has overcome. Okay? Has overcome. Like the activation energy barrier has overcome. due to the increase of kinetic energy. Right? Those are the two factors. So number of collisions has increased due to the kinetic energy increase. Activation energy barrier has overcome due to the yes. Right? That's a simple way of remembering. And next is what? Nature of the reactant. So when it comes to the nature of the reactant, that means if it is solid or the crystal or powder, right? This crystal or powder. That's what the nature of the reactant is. If it is in the solid, liquid, gaseous, the phase of the matter, right? Is it in the crystal? Is it in the uh, powder? Yeah. Yes, because it's about the surface area as well, right? So like if it is gas, more surface area. Compared to gas, liquid is less surface area. Compared to liquid, solid is less surface area, right? And compared to powder of the solid, powder is more surface area than the crystal. So more the surface area, the probability of reacting is high because it's everywhere, spreaded, isn't it? If it is spreaded, probability of reacting is high because if it is in the solid or the crystal form, there are so much of hindered particles, like the middle particles are hindered in the sense like it's hidden. Yeah, it's not like open, exposed to the reaction. So it's hindered. So the hindered particles won't be allowed to react, right? So when you like increase the surface area, which means you powdered it, there will be more surface area to react. So the number of or the probability of reaction will increase, the surface area increases. Therefore, the rate of reaction will, you have to remember that. The third one is presence of catalyst. Now, I think we discussed more about the presence of catalyst under enzymes, biochemistry, right? And did I explain you there's like one theory called lock and key method? I think I did. One of the paper. Lock and key method is there. I'll explain it again. Like presence of catalyst is this. It's like a matchmaker. What does a matchmaker do? He goes and connect two of the people. And once the reaction occurs, the matchmaker doesn't stay with the couple. Yeah, he goes away and he connects two of another couple. Right? It's like a matchmaker. The matchmaker has the correct mold for these reactant to connect. Get it? Like he's friends with the girl and he's friends with the boy as well. So he has a mold to connect both of the reactants, right? And once two of the reactants connected with two of the molds in the catalyst for the matchmaker, what will the matchmaker do? The matchmaker will connect those two, right? So the mold or the shape for two of the reactants is there in the catalyst. Once the reactants are connected to that mold, it will connect that two, and once the reaction occurred, it will get away and go catalyze the other reaction. That's what happens. Okay. So in the presence of catalyst, what actually happens is the activation energy barrier is reduced. Energy barrier is, yeah, or either the reaction will be taken in a lower activation energy pathway. Like let's say there were one boy and a girl, they never knew each other, or they knew each other, but they were never sort of like connecting each other. But the catalyst made it easy, right? If they were to connect each other, that might will take a long time or a long like huge energy. But the catalyst made it easy, like so he took it in a different pathway, that is the energy is low, right? That the energy is low. Get it? And the lock and key method is the catalyst only can connect a certain specific reactants only. Like in the sense, let's say the catalyst, for to catalyze the reaction of maltose breaking into glucose, the catalyst only can connect with maltose only. Okay? It can't connect with any of the sucrose or lactose. Is specified. That is lock and key method. So the lock key is the catalyst, the key is the maltose. So maltose only connect with the catalyst of the maltose, right? The maltose catalyst cannot connect with any of the sucrose or the lactose. There is lock and key method. They are like specified for a certain molecule to react. The catalysts are very specified, like enzymes are very specified catalyst, right? Enzymes are very specified catalyst, which means it cannot catalyze any of other reactants except for what it's meant to catalyze. Get it? Right? There is lock and key method, like that's extra out of this one. The presence of catalyst is that it's what is the presence, what happens in the presence of catalyst? The reaction is occurred in a low activation energy pathway, therefore the rate of reaction is. So the other one is concentration. Concentration again is more number of reactants. There's more number of reactants, the probability of reacting is high, right? And when it comes to the gaseous reactants, pressure, think of it in this way. Now, you just only have to remember is when the pressure increases, the probability of reaction is increasing, therefore the rate of reaction increases. Pressure increases, probability of rate of reaction increases, probability of reactants react is increases, therefore the rate of reaction increases. But what actually happens is, think of a balloon, right? Reactants are inside the balloon. You increase the pressure, what will happen to the volume? There's a balloon, you increase the pressure, what will happen to the balloon? The volume decreases. Volume decreases means the gas is what? Concentrating, isn't it? The gas is concentrating because the volume is reducing, the gas becomes concentrated. It's again increasing the concentration. Understand that? Pressure is increasing, pressure is again increasing the concentration. Get it? So high pressure means concentrating. Rate of reaction වැඩි වෙනවා. Probability එකකින් වැඩි වෙනවා. ඒ කියන්නේ probability of number of collisions, because there's more. That is probability of colliding the reactants. So the rate of reaction. Get it? Right. Then the concentration and time graph. Right. Concentration and time graph. Or how the concentration of a reaction change with time, right? So this is concentration, right? This has time. This is time. So let's say A plus B is reacting to produce C, right? A plus B reacting to produce C. So what can you tell about the concentration? Let's take the stoichiometry as well. I'll take this as 2. Right? So now, what can you tell about the concentration of A by the time? Concentration of A is Yeah, reducing, decreasing. But does it decrease linear? Does not. Why? Yes, gradually decreases. I'm asking, it's not reducing linearly, reducing in a curve. Why is that? Which means, like, at the beginning, the rate of reaction is high. At the end, rate of reaction is low. Why is that? We'll draw it first. We'll draw it first. Like, forget this reaction. The concentration time graph is anyways this. Because now at the beginning, rate of reaction is high because in a very small period of time, a huge concentration is changed. Yes. In a very short period of time, huge concentration is changed, which means at the beginning here, R is really high, right? But at the very end of it, there's only a very small concentration difference, right? Very small concentration difference, but the time is really high. T1, T1, T2, T2, T1, T1. If you consider this part, R equals delta C2 minus delta T2, which is very low because the time difference is high, but the concentration difference is low, right? So why does it happen this way? At the beginning, rate of reaction is really high. At the end, rate of reaction is very low. Why is that? Because the rate of reaction depends on what? Concentration. Now at the beginning, concentration is high. At the end, concentration is very low. So at the beginning, because high concentration, rate of reaction is high because more probability is there. Now at the end of it, probability is less because less molecules, right? The rate of reaction is, this is the graph. You understand that? This is important, huh? Let's come to uh, the rest of the other graphs, right? Concentration and time. Let's say A2A plus B is reacting with C. Now this is concentration and this is time spent. And the concentration of A changes how? Like in this one, concentration of A is reducing. So let's say concentration of A is like this. So it was yeah. මැද්දට ඇඳලා තිබ්බොත් කියලා කියන්නේ මේක තාම එන්ඩ් වෙලා නැහැ. රියැක්ෂන් එක යනවා තාම. 0 එකට එන්න ඕන කියලාද කියන්නේ? ඒ කියන්නේ මේ අඩියට ගෑවෙන්න. කියන්නේ concentration 0 වෙන්න. ඔව්. දැන් මේක මේ මම මේ දාලා තියෙන පොතෙන්නේ. පොතෙන් දීලා තියෙනකොට එහෙම නෙමෙයි. right? So like මේකේ දීලා තියෙන පොතේ තියෙන එක නම් එහෙම completely දීලා ඕනේ. ඒ more accurate 0 වෙනකන් අදින එක ඒක හරි. අපි මේ consider කරලා තියෙන reaction එක තාම ඉවර වෙලා නැහැ කියලා. There's a long way to go. ඒක උඩට ගන්න එපා, පල්ලෙහාට තමයි එන්න ඕන. පල්ලෙහා පැත්තට තමයි යන්නේ ටික ටික. උඩට ඉන්නේ. That's the only difference. පල්ලෙහාට තමයි යන්නේ. And what about the B? B එකත් එහෙම තමයි. හැබැයි B එකේ amount එක අඩුයි. යාට වඩා පල්ලෙහාම පටන් ගන්න මෙහි. හැබැයි යා 0 එක පැත්තට තමයි හිට් වෙගෙන යන්නේ. B. And what about C? Comes from down to the top level, but oh, if it ends, it should be like B and C දෙන්නගේ එකම amounts නේ 1 to 1 නේ. ඒකින්ද ඉවර වෙනකොට නිකන් එයාට කිට්ටුවට තමයි එන්න ඕන නේ. එයාගේ පැත්තට තමයි ඒකෙන් එන්න ඕන. right? like huh? තේරුන්නේ නැහැ. right right right. So now the next is if I change these factors affecting rate of reaction, how does it affect the graph is the next question. The factors affecting the rate of reaction එක අපි graph එකේ තියෙන factors වෙනස් කරොතින් sorry rate of reaction එක change වෙන factors වෙනස් කරොතින් කොහොමද graph එකට effect වෙන්නේ කියන එක. My next. So take it. Concentration. Now what are the factors? Temperature, yeah. Think if I change the temperature, right? Think if I change the temperature. If I change the temperature of, let's say, now the graph is concentration and time anyways. And this is the usual graph of, let's say, A and B. I'll take only A and B. This is the usual graph of A and B. This is the usual graph of A and B. This is A and this is, oh no, it should be C, right? This is C. This is C because it's the product rate. When you increase the temperature, the rate of reaction increases. How? Does the initial and final change? Initial and final amounts change? No, right? Initial and final amount doesn't change because it's the same initial amount and the same final amount. So how does speed up when the temperature වැඩි කරාම? How does it speed up? By reducing the time it takes, which means the graph is leaning more towards where? To the less time axis, right? Less time axis, which means graph is more lean toward the less time, but the initial and the final are same. And even for the A, it's more lean towards the less time. Graph is more lean towards the less time, which means the rate of reaction has increased. This has a higher rate of reaction than A. This has a higher rate of reaction than. You understand that? කොහොම graphs එන්න පුළුවන් identify කරන්න. So this is high temperature. This is low temperature, right? In high temperature and low temperature. Get it? So the next is the Boltzmann curve, right? Boltzmann curve. ඒක විතරයිද ගහලා තියෙන්නේ? හරි. අරක දෙකක් දාලා තිබ්බේ. බලන්න. තියෙන ටියුට් එකයිනේ තියෙන්නේ. ටියුට් මම දෙකක් දාලා තියෙනවා. Thank God he was online. Ashin, thank you. Right. So this is the fraction of molecules. Right. This is the Boltzmann curve of a normal reaction, which is like very small fraction is in high energies and very small fraction in low energies, and the number of molecules that are really high is at a very average energy, right? Average energy के तीन molecules are very. Activation energy is here, right? And the molecules which have overcome the activation energy is now reacting. So the lines which I have drawn in yellow are the number of, like the area of this yellow part is the number of molecules that is reacting. Now when I increase the temperature, the graph will move towards more energy side, right? The graph will move towards more energy side. Get it? Now when the graph is moved towards more energy side, the number of molecules have overcome the activation energy is now more, which means they're reacting more, right? So this is what? How temperature increase rate of reaction, right? This is how temperature increase rate of reaction. Okay? How has it increased it? By increasing the fraction of molecules have overcome the activation energy, right? The next is fraction of molecules, right? And this is energy. May they give me energy in no. This is energy as well. And this is the normal Boltzmann curve, which is like number of molecules in high energy is very low. Number of molecules in low energy is very low. The fraction of molecules in average energy is the highest, right? And what happens when you put a catalyst? Usually the activation energy is this, right? This is the activation energy usually, right? And when you put a catalyst, what does the catalyst do? It takes the reaction in a low activation energy pathway. So the activation energy becomes low. So now all the molecules have overcome this activation energy, now is reacting. This is the amount reacting now. Get it? So initially only this was reacting, now this much is reacting. So how this is how activation energy, sorry, this is how catalyst increase rate of reaction, right? This is how catalyst increase the rate of, understand? Then the last is multi-step reaction. Okay. So like when there is no catalyst, so yeah, make EA1 එක තමයි no catalyst. When there is a catalyst, there is no catalyst. Oh, make it no make it. Aditya. Right? Next is multi-step reaction. And multi so yeah, before that, before that, min මේකත් බලාගන්න. මේ graph එකත් බලාගන්නකො. මේකත් බලන්න. Rate of reaction, right? Concentration of substrate. Maybe concentration of substrate. Right? And let's say there's a certain amount of enzymes in this one. Right? There's a certain amount of enzymes in this one. So at the beginning, there are 10 enzymes, and let's say I'm only putting one substrate. Right? There are 10 enzymes in the beaker, and I'm putting one substrate. So what will do? The substrate will be reacted. If I put two of the enzymes will come and will react and finish. Right? If I put three of the enzymes will come and react. So by the time I'm increasing the concentration, the rate of reaction increases. Why? Because per time the number of molecules that are reacting and producing products are increasing. Yes. And if I come to 10, now 10 of the molecules are put, 10 of the molecules are reacting. The rate of reaction is 10. And now if I put 11, can 11 be reacted at the same time? Still only 10. And if I put 20, can 20 be reacted at the same time? Still only 10. If I put 30, so 10 at a time. So it will become constant in rate, right? So at the beginning, the rate of reaction will increase, and when the enzymes are saturate, rate of reaction will constant. So I increase the substrate concentration furthermore, right? So at this point, what happens? Enzymes or the catalyst are saturated. Get it? All of the enzymes or the catalysts are now saturated. So it becomes constant. But at the beginning, more enzymes plus reactants, rate of reaction is gradually increasing and becomes constant when the enzymes are saturated. Get it? Now come to the multi-step reactions. Multi-step reaction is like the reaction occurs in more than one step. Let's say I want to produce A plus B into D, right? I want to produce A plus B into D, right? But this whole reaction doesn't happen in one step. Instead, this is what's happening. A plus B is reacting and producing C plus E, right? Or let's say C is produced. Now the C is reacting with A again and producing E. And the E is reacting with B again and producing C. Sorry, producing D. D is the last one. So now A plus B into D is the total reaction, but it didn't happen in one reaction. Instead, it went through three of the reaction. Right? So what happened here? If I want to take the total reaction, I have to add all of them together, right? So if I add all of them together, what happens here? How many A's are there? A, A. Two A's are there. Plus, how many B's are there? Two B's are there. How many C's are there? One C is there. How many E's are there? One E is there. So in the product side, one C, one E, one D, right? So there's C and E in the product and reactant side. Now what has happened here? The products produced has used back again to react, isn't it? So what should happen? C to C and E to E cancels out, which means the reactor, the products produced were used as reactant in the next reaction, which means they are produced in the middle, reacted in the middle. So they don't belong into the main reaction. Because what do you call them? We call them the intermediate products. Call them the intermediate products. So these two are what? Intermediate products. These two are the intermediate products, right? And sometimes this also can happen, right? And this also can happen. But in the same reaction, right? In the same reaction, let's say Z is there. Z plus A plus B produces C. Z is released. And again Z comes to the next step. Plus C plus A produces E. And Z is again released. And E plus B. So here again the Z is there. E plus B produces D. Again the Z is released. So now in this one, these are intermediate products. Why? They were produced in the middle, right? In the beginning of the reaction, it wasn't there. It was produced in the middle. It's a product. But is it produced in the middle? No, it was there in the beginning. Now it's there in the end as well. What is that? That's a catalyst. Get it? Is a catalyst. Is a catalyst. Get it? Because they are in the beginning, they are in the end, right? It's not the intermediate product. It's a catalyst. Good. Right. It is a catalyst. And the last one is in a multi-step reaction, out of these three reactions, right? A plus B is producing C, right? Then the C plus A producing E, and the E plus B producing D. Out of these three reactions, 1, 2, and 3, right? This is fast, this is medium, this is slow. So out of these three, which one determines the rate of reaction? The slowest one determines the rate of reaction. We discussed it like in this way. There's a straight road, only one vehicle go at once. There are Bugattis, Ferraris and everything. But there's a no. Now there's a like what do you call it? There's a cart, right? There's a cart as well, right? So now, though all the other vehicles can go faster, which is determining the speed of this line of vehicles? The cart, because one vehicle only can go once, right? So until the cart finishes its travel, all the others have to, right? So likewise, the speed of reaction or the rate of reaction is determined by the slowest step, right? So the rate of or the speed of reaction is determined, right, by the slowest rate of reaction is speed of reaction is determined by the slowest reaction. Yeah. Sure. Oh, understood it? So that's it. Short, right? Not very much. Hope it's short. Sorry. So let's finish, shall we? Today. Session, I'll see you. Study well and do the papers as much as possible.